Hello, my name is Tárik Salem, and I'm presenting our work with the title Prediction Intervals, Split Normal Mixture from Quality-Driven Deep Ensembles. The work was done with Helge, Langseth, and Heri Ramampiaro from the Norwegian University of Science and Technology. But before I present our method, I'll give you a brief introduction to the sources of predictive uncertainty, to prediction intervals, and to the related work we build on. The sources of predictive uncertainty can be decomposed into aleatoric and epistemic uncertainty. The aleatoric uncertainty cannot be reduced by the model or data as it originates from the irreducible data noise. For example, due to measurement errors. Although not possible to reduce, it's possible to capture it. On the other hand, epistemic uncertainty can be in principle reduced through model or data, but it's often difficult. It can be caused due to model bias and due to data bias. Prediction interval is a way of expressing predictive uncertainty in regression analysis. Prediction interval tells us that the future observation y will fall within the prediction interval boundaries yl hat and yu hat with a certain probability, gamma. Gamma describes the desired coverage probability, but we often refer to alpha that is equal to 1 minus gamma. For illustration, assume a true signal that is unknown to us. Here it's a sine wave. What we usually measure is data with irreducible noise. And since we know the generative process of this data, we can also visualize the ideal prediction intervals, here with 95% coverage. However, this is also usually unknown in the real-life setting. Given the noisy data, our aim is to approximate the ideal prediction intervals. Our method heavily relies on the quality measures of prediction intervals. Prediction intervals are usually evaluated with respect to the coverage probability, the PICP measure, and with respect to their width, the MPIW measure. We generally aim to generate prediction intervals as narrow as possible, but maintaining the desired coverage probability. That means we wish PICP to be equal or greater than gamma. Although methods adopting Bayesian approach in the context of neural networks provide sound results, in this work we explore a non-Bayesian but probabilistic alternative. Our work can be considered as friendly continuation of the work presented by Pierce et al. In 2018, which is primarily inspired by the findings of Horsavi et al. From 2011 and Lakshminarayanan et al. From 2017. The original approach by Pierce et al. Is introducing the quality-driven loss function, which integrates MPIW and PICP measures. Given the LQD loss, an ensemble of neural networks is trained. The ensemble of neural networks is then used to generate prediction intervals, here illustrated using our toy example. As next step, the ensemble of generated prediction intervals is aggregated in order to generate the final prediction intervals that account also for epistemic uncertainty. As you can see, this is done independently for the lower and upper bounds. The mean of the lower and upper bound is calculated. The multiple of the SEM, standard error of the mean, is subtracted or added respectively. And this results in the final prediction intervals. In our paper, we call this method SEM-QD, SEM standing for the aggregation method and QD for the loss function. It was shown that this distribution-free method can generate prediction intervals of a good quality. However, it has three main limitations that we have addressed in our continuation. First, the inability to generate point estimates. Second, the theoretically weakly justified method for aggregation of ensembled prediction intervals. And third, the fragile training process that has been noted also by the authors. In our method, SNMQD+, we slightly modify and retrofit the original loss function by adding MSE loss for point estimates. And we add the very important penalty function LP that enforces the semantic integrity of the output and also stabilizes the training process of the neural networks. As illustrated, it gives us the capability to generate an ensemble of point estimates. Now to our aggregation method that generates the final prediction intervals. Here we fit each prediction interval and point estimate in an ensemble to a split normal distribution, also known as two-piece normal. Split normal distribution is simply an asymmetric normal distribution allowing for two different standard deviations for the left-hand and right-hand side from the mode. We find the two parameters for standard deviation, sigma 1 and sigma 2, by optimizing the LSN loss that also considers the desired coverage probability. After fitting the split normals for each output, we calculate the mixture of split normals for each ensemble, as illustrated in the plot. And from the split normal mixture, we calculate the final prediction intervals, accounting also for epistemic uncertainty. The final point estimates are calculated as simple mean. We run our experiments on 10 UCI datasets. In all cases, we train and assemble 5 two-layer neural networks, and for most datasets, we perform 20 trials. The desired coverage probability, or gamma, was set to 0.95. We compare our method SNM-QD+, against the original method SEM-QD, and also against MVE, mean variance estimator, which returns a parameterization of a normal distribution. And we have also compared our aggregation method SNM with original aggregation method SEM on the same ensembles trained with our QD plus loss function. In this table, we see the evaluation of the prediction intervals. We can see that our method SNM-QD plus is delivering well-calibrated prediction intervals. Compared to the original aggregation method, SEM, we can also see that our aggregation method, SNM, generates more narrow prediction intervals while maintaining the desired coverage probability. In this table, we see the evaluation of point estimates. And we compare it also against an ensemble generating point estimates only, labeled as MSE, because of the loss function. We would call our results of our method as competitive compared to MSE and better compared to MVE. This table shows that the training process is very reliable if trained using our QD plus loss function. And this is largely contributed to the penalty function. This we can clearly see in our hyperparameter sensitivity analysis. It was performed on the yacht dataset. We have analyzed the PICP, normalized MPIW and MSE with respect to the changes in hyperparameters lambda 1, lambda 2, and xi. The hyperparameter xi scales the penalty function, and if set to 0, the penalty function is disabled. The gray area stands for non-converging training process or semantically incorrect outputs, such as prediction interval crossing or point estimates out of prediction interval bounds. It clearly demonstrates the critical importance of the penalty function, and it also results in better behaved hyperparameter landscape. Overall, we see our method as a fair extension of the practitioner's toolset for quantifying predictive uncertainty in regression tasks. For more details, check our paper and our implementation on GitHub. And thank you for your attention.